Civil Engineering and Architecture. Mr. Voigt here. I'm going to go over with you kind of complicated computation that Project Lead the Way has us done for designing a beam. Now we're going to do our exercises talking about a hotel's second floor. Um, but there will be an assignment for you to do this for your Keystone library. So I just drew this little diagram. This should be familiar to you. The diagram, these are just dimensions on the other sides of these two lines here, right? So you should remember that, like the number 1 here, that is an interior beam, right? And the number 2 is an interior girder. Beams attach, see, this beam would attach to this girder there, this beam would attach to the girder there, this beam would attach to that girder there, and so forth. So this is a girder. So there's 4 internal girders, and there's a whole bunch of internal beams. 1, 2, 3, 4, 5, 6 times 3, like 18 internal beams. This is an external girder, and this is an external beam. So this is an external beam, this is an external beam, this is an external beam, so forth. Okay, so why is this important? A few lessons back, when we did loading, we loaded these. So remember, an internal beam here is going to have a tributary that big, right? So the tributary of that beam is the same as the width between the beams, right? Because you go halfway between them and halfway between them, and that ends up being the same. The tributary for an external beam, however, there's nothing on this side, so it's just halfway between the beams on the inside. So it's half of this width for its tributary. For the girders, it's the same. Halfway this way and halfway that way would be the tributary for that girder. For this exterior girder, it's just halfway this way. So this is going to hold half as much as that. Anyway, when we do our loading, which is going to be the first thing we do in this activity, we're going to be referring to these. So our first activity, we need to figure out all the things we're going to do in these steps for each one of these types of beams. Because what the whole idea is, we figure out exactly what beam is it that we are going to put in our design. I mean, specifically, a wide flange 12 by 13, a wide flange 14 by 18, what is it? Okay? So that's what we're doing in this exercise, choosing the actual beam that goes in all of these different 4 places. And in order to do that, we have a whole series of things that we have to do for each one of those. So the first one we're going to do is our interior beam right here. So we're going to say interior beam. Okay? So the first thing we're going to do, and I need to show you, I handed you this packet. So the first, and this is the list of things we do, right? We calculate the loading, then we create a beam diagram, then we calculate the end reactions, and so forth. So we're going to walk down this list. I'm going to try to number them according to this list. Now, they do get numbered, unfortunately. I also handed you this packet, and in the assignment, they number them slightly differently because they kind of give you the same list right here. They do give you the same list. But when we start going through them, like here and here, whoops, like right here, they kind of combine some of them. So if you're numbering them and you want to stay on the right number, we're going to go ahead and stay with these numbers right here. So number 1, calculate the loading. All right, so how do we calculate the loading? Here's our loads right here. So for our interior beam, it is going to carry 50 pounds per square foot of dead load and 100 pounds per square foot of live load. Okay, so that's 100 pounds per square foot. Now, that's for every square foot. So what you have to do is figure out how many square feet there are. So what you do is you take the tributary, because remember, it goes from here to here. That tributary is going to be 6 feet, 8 inches wide. Or if you express it all in feet, that is 6 2/3, right? 6.67 feet is the tributary. So what you do is you take your pounds per square feet. So we're going to say dead load equals 50 pounds per square feet times our 6.67, right? And then and that's feet. And then we're going to go live load, and we're going to go 100 pounds per square foot. Times our 6.67. And I have a calculator here. I'll do some calculations. I already know what this one is. I have already done it. So I'm just going to write it in here. If you really want to type that into your calculator, go ahead. 333.5 pounds per linear foot, or pounds per foot, either way. Okay, so what ends up happening, this is feet, this is pounds per square feet. So this is be pounds. So your feet cancel out, and you're left with pounds per foot. Okay, this one is going to be 667 pounds per linear foot. So it gets a little bit confusing on the units here, but basically it's for every foot of beam I have, which is going to be 18, right? For every foot of beam I have, I'm going to be carrying, for my live load, 667 pounds. For my dead load, 333.5. So what you have to then do is add these together. And it's going to come out to 1,000.5 pounds per linear foot. Okay, so that's per linear foot. Well, how long is our beam? I'm going to round this, by the way, to 1,000 instead of. So we're going to say 1,000, and our beam is 18 feet long. So our total load, and this is pounds, our total load here is 18,000 pounds. So I wrote this differently. Just understand those are the same thing. Okay, so 18,000 pounds per foot. But if you remember, well, no, that's just our loading, right? We'll deal with that later. I'm sorry. I should just leave it. So our total loading is for each beam. So this beam is going to carry 18,000 pounds. This beam is going to carry 18,000 pounds, and so forth for all our interior beams. So that is number one. Next, create a beam diagram. You guys should already know how to do that. So number two, you're just going to go beam diagram. We always put our RYA here. We always put our RYB there. Remember, those are shears. And we always go RXA equals 0. Now, it's worth noting that our dead load and our live load, we treated them as if they were uniform loads. Okay? That they were just spread out evenly. So our total, and remember, we represent our uniform loads with a W, and that's 1,000 pounds. So that's our uniform load. So that is our beam diagram. The only other thing we need in here is, this is 18 feet long, right? Okay, so that's our beam diagram. Pretty simple. Number three for us is calculate the end reactions and calculate the maximum moment. I'm going to go 3 and 4 because I'm going to well, maybe I'll do them separately. 3, end reactions. If you have remember, we boiled down our end reactions to these formulas. Well, we're in a uniform load beam, so this is our end reaction. RA equals RYB equals WL over 2. So I'm going to write that here. RYA equals RYB equals WL over 2, which equals, our W is 1,000 times 18 divided by 2, which equals 18,000 divided by 2, which equals 9,000 pounds. So my RYA is 9,000 pounds and my RYB is 9,000 pounds. Okay, when they're uniformly distributed, each end is going to hold the same amount of weight. Okay, so that's my end reaction. Number 4, it was my moment. And again, we boiled down our moments to these formulas. So M max equals WL squared over 8. That is our moment for a uniformly loaded beam. So WL squared over 8 equals 1,000 times, what's 18 squared? I just like to go 18 times 18 equals 324 divided by 8, equals 324,000 divided by 8, which equals, I'll go ahead and do it on here, 324, 40,500. Now, we should know by now this is foot-pounds. So our max moment is 40,500 foot-pounds. So it needs to, that 18,000 pounds of loading that we have designed for is going to exert 40,500 pounds of bending force on these beams. It's also going to distribute 9,000 pounds of end reaction on each end. That means that those beams will have to be held at least 9,000 pounds of strength at each end. And it's going to have to resist 40,500 pounds of bending force when it's fully loaded. Okay, so we need a beam that can handle at least these numbers. They can handle more than this, but they can't handle less, because if they handle less, they might fail. So that's what we're doing. We are choosing a beam that will meet these requirements. Okay, so the next step. This is going to do one more, and then this video will be over, and I'll make a second video. Calculate the required nominal moment. Okay, so what this means is we've figured out the maximum moment that from a design point that we need. However, we usually design our beam to hold more than the maximum of what we think the loading will provide. So that's what we're going to figure out under number 5. So number 5, if you turn in this packet, it is the first time that you're going to use some formulas I have in here. Now these are just informational. We don't actually use these formulas. They're there for, this is like the overall allowable strength design that we're using. Just for now, don't worry about those. We start right here, the allowable bending strength. So what we do is we take what we need in our design strength, and then this omega means a safety factor. And in this case, bending safety factor is 1.67. So we end up using this, and I'll show you. So we're just going to copy this formula over. So Mn equals Ma, and Ma is our number here. This is our loaded number. And omega is our safety factor, which they gave us right here, times omega. So Mn equals 40,500 foot-pounds times 1.67. Okay, and so what that means is, I'm going to go ahead and do this, 40,500 times 1.67, and I get 67,000. So Mn equals 67,635 foot-pounds. So the last thing I'm going to tell you on here is, what this means is, even though our load is only going to exert 40,500 foot-pounds, of bending force on this, we design our beam to hold at least 67,635 foot-pounds just to be safe. That's what this one, we multiply what we need by 1.67 and we over design. So we make sure that it will hold our design and even a little bit more. This is common practice in engineering. You have a safety factor over designing things to make sure that they won't fail. Okay, so we're going to stop there. We're going to pick up with number 6 in the next video.